March 17th, 1943, Bay of Biscay, 18,000 feet above the Atlantic. The cathode ray tube glowed green in the darkened nose of Wellington bomber H-538 as Sergeant Michael Harrington watched the sweep line rotate across the display. Nothing, just the endless clutter of wave returns, the electronic noise that made every patrol a test of patience and skill. Then, at 9 miles out, a blip appeared. Sharp, distinct, unmistakable. Harrington's hand moved to the intercom switch, his voice tight with controlled excitement. Contact. Bearing 270. Range 9 miles. Surface target. The Wellington banked hard, descending through the night. In the darkness below, U-boat crewmen continued their transit across Biscay, confident in the technology that had kept them safe for months. Their Metox detector, mounted in its wooden frame on the conning tower, remained silent. No warning beeps, no indication that electromagnetic radiation was painting them from above. They had no idea that the rules of the game had changed completely, that the radar scanning them operated at a wavelength their detectors could not see, that they were visible to enemies they believed to be blind. The Lee light failed. Technical malfunction at the moment of attack. Harrington watched the U-boat slip away into darkness, his frustration tempered by a different realization. The new radar had worked exactly as promised. 9 miles detection range against a surfaced submarine on a system the Germans could not detect. This was not a minor improvement over existing technology. This was electromagnetic dominance made real. What neither Harrington nor the U-boat crew understood that night was that this single contact represented the culmination of discoveries made by radar operators, technicians, and captured prisoners whose innovations, both official and improvised, were about to transform the Battle of the Atlantic. Within 8 weeks, these advances would destroy nearly 30% of Germany's operational U-boat force. Within 3 months, Admiral Karl Dönitz would withdraw his submarines from the North Atlantic entirely, conceding defeat in the campaign that had nearly starved Britain into submission. The story of how this happened is not about scientists in laboratories or admirals planning strategy. It is about the radar operators who discovered that progressively reducing transmission power could deceive enemy detection equipment. It is about the technicians who realized that a captured RAF officer's testimony, deliberately crafted in interrogation, had sent German countermeasure programs down a false path for 8 critical months. Most fundamentally, it is about how a handful of men, working with equipment they barely understood, exploited properties of electromagnetic radiation to create tactical advantages that rewrote naval warfare. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. January 13th, 1942, RAF Ballykelly, Northern Ireland. The test aircraft descended through heavy clouds, its radar operator scanning the display for the submarine HMS Tightlark positioned somewhere in the Irish Sea. At 12 miles range, the contact appeared, clear, sharp, far superior to anything the older radar systems could achieve. Philip D., watching over the operator's shoulder, noted the result with satisfaction. The new centimetric radar based on the cavity magnetron worked exactly as theory predicted. But theory was cheap. The Royal Air Force had possessed theoretical understanding of shorter wavelength radar for years. What it lacked until now was the industrial capacity to produce magnetrons in sufficient quantities and the operational experience to deploy them effectively. The path from laboratory demonstration to combat deployment would prove far more complex than anyone anticipated, delayed by bureaucratic battles, resource constraints, and the learning curve inherent in revolutionary technology. The magnetron itself had been developed in 1940 by John Randall and Harry Boot at Birmingham University, solving the fundamental problem that had constrained radar development since the technology's invention. Earlier radar systems operated at wavelengths of 1.5 meters, requiring large antenna arrays and generating relatively weak signals. The magnetron could produce powerful microwave pulses at wavelengths of 10 centimeters, allowing compact antenna designs with dramatically improved resolution and range. By June 1940, General Electric Company had produced sealed magnetrons suitable for aircraft installation. The technology had been shared with the United States during the Tizard mission in September 1940, leading to American development programs at MIT's Radiation Laboratory. The potential military applications were obvious to anyone who understood electromagnetic physics. Shorter wavelengths meant smaller antennas, better target discrimination, and the ability to detect objects that longer wavelength systems would miss entirely. Yet 3 years elapsed between the magnetron's invention and its deployment on anti-submarine patrol aircraft. The reasons for this delay reveal much about wartime priorities and institutional conflicts that sometimes mattered more than technical capability. RAF Bomber Command wanted the magnetrons for H-2S terrain mapping radar, allowing bomber crews to navigate and identify targets through clouds and darkness. This application promised to make the strategic bombing campaign effective regardless of weather, transforming a fair-weather force into an all-weather threat. Bomber Command, under Air Chief Marshal Arthur Harris, fought viciously to maintain priority access to magnetron production. RAF Coastal Command, responsible for anti-submarine warfare, argued that the technology could break the U-boat campaign in the Atlantic. By early 1942, German submarines equipped with Metox radar detectors could hear the transmissions from existing ASV Mark II radar at ranges far exceeding the radar's own detection capabilities. U-boats would dive long before aircraft could close to attack range, rendering night patrols largely ineffective. Centimetric radar operating at 10 cm wavelength would be invisible to Metox, which could only detect signals in the 1.5 meter band. Surprise attacks would again become possible. The bureaucratic battle consumed months. Bomber Command won initially, claiming all magnetron production for H-2S systems. Coastal Command protested that the submarine threat might strangle Britain's supply lines before strategic bombing could affect Germany's war-making capacity. The debate reached Churchill, who attempted to broker compromise. Resources remained insufficient to supply both commands adequately. Engineers worked frantically to increase magnetron production, while commanders argued over allocation priorities. The situation reached crisis in summer 1942, when Metox deployment became universal among U-boats. Coastal Command's effectiveness collapsed almost overnight. In June 1942, before Metox became widespread, aircraft equipped with ASV Mark II could detect surface submarines and attack before the U-boats could dive. Statistical analysis showed that radar-equipped aircraft found U-boats after 95 hours of flight time on average, compared to 135 hours for aircraft without radar. By October 1942, after Metox deployment, the detection rate for radar-equipped aircraft had deteriorated to 135 hours, identical to aircraft without radar. The technology that had given Coastal Command its edge had been completely neutralized. U-boat commanders described the transformation in their war diaries. Kapitänleutnant Hans-Joachim Schwantke, commanding U-43, filed a report in December 1942 detailing an attack in the Bay of Biscay. His boat had been running on the surface at night to recharge batteries when searchlights suddenly illuminated from directly overhead. No warning from Metox, no engine noise, no indication of approaching aircraft. Only frantic anti-aircraft fire and an emergency dive had saved them from depth charges that bracketed the boat as it submerged. "We were told Metox would give us minutes of warning," Schwantke wrote. "Instead, we had seconds. Either the British have developed radar our detectors cannot sense, or they possess some other technology we do not understand. Whatever the answer, we are being hunted by enemies we cannot detect until the moment of attack." His analysis was partially correct. The British had not yet deployed centimetric radar on anti-submarine aircraft. What Schwantke had experienced was a ley-light attack, the powerful searchlight developed by Wing Commander Humphrey de Verdelais to illuminate submarines after radar contact was lost at close range. But his conclusion that British technology had advanced beyond German understanding would prove prophetic within months. By late 1942, shipping losses to U-boats had climbed to unsustainable levels. In November, German submarines sunk 119 merchant ships, totaling 729,000 tons. The exchange rate, measured in tons of merchant shipping sunk per U-boat lost, heavily favored Germany. At current rates, U-boats would sink Allied ships faster than American and British shipyards could replace them. The tonnage war, which would ultimately determine victory or defeat, was being lost. Admiral Karl Dönitz, commanding Germany's submarine force, studied the statistics with grim satisfaction. Metox had restored the tactical advantage his U-boats had enjoyed before radar deployment. Allied aircraft could no longer surprise submarines at night. The vast expanses of the Atlantic provided concealment during daylight hours, when aircraft could still locate U-boats visually. Wolfpack tactics, using multiple submarines to overwhelm convoy defense, were achieving remarkable successes. The string of victories led Dönitz to believe the Battle of the Atlantic could still be won, that Britain could be starved into surrender before American industrial production tipped the balance irreversibly. What Dönitz could not know was that his moment of maximum confidence coincided with the technological revolution that would destroy his campaign. In December 1942, Robert Hanbury Brown had finally convinced the Air Ministry to adapt H-2S radar for anti-submarine use. The system, designated ASV Mark III, differed from H-2S, primarily in antenna configuration. The bomber version used a rotating scanner in a ventral dome to create terrain maps. The anti-submarine version optimized the scanner for surface search, with modifications to improve detection of small targets like submarine conning towers against sea clutter. 2 prototype systems were sent to No. 30 Maintenance Unit for installation in Wellington Mark VII bombers. Testing began at the Coastal Command Development Unit in January 1943. The results exceeded expectations. Detection range against surfaced submarines reached 14 miles under ideal conditions, nearly double the effective range of ASV Mark II. Even semi-submerged U-boats, showing only their conning towers, could be detected at 7 miles. Most critically, the system operated at 9.1 centimeter wavelength, completely outside the detection range of Metox. The German radar warning receiver, tuned to detect signals between 1.3 and 2.6 meters wavelength, was electromagnetically blind to centimetric radar. The Metox antenna, a wooden frame called the Biscay cross due to its shape, could not receive signals at such high frequencies. The receiver electronics lacked the bandwidth to process centimetric wavelengths, even if the antenna could somehow detect them. German U-boats equipped with Metox believed themselves safe from radar detection, when in fact they were completely vulnerable to a system they could neither detect nor counter. Production and training moved with unprecedented urgency. Ferranti had predicted spring 1943 delivery at the earliest, but political pressure and the worsening Atlantic situation accelerated development. By late January 1943, initial production units were arriving. The challenge shifted from manufacturing to training. Radar operators familiar with ASV Mark II needed to learn an entirely different system. The cathode ray displays looked similar, but operated differently. The interpretation of contacts required new skills. Sea-return clutter, always a problem with radar, behaved differently at centimetric wavelengths. RAF Station Clinton in Ontario, Canada, graduated 110 radar technicians specifically to maintain ASV Mark III systems. These specialists received training on similar American-designed DMS radar sets before deploying to Coastal Command squadrons. The maintenance challenge was formidable. The magnetron, while revolutionary, was also temperamental. Vibration from aircraft operations could damage the delicate cavity structure. Temperature fluctuations affected performance. Operators needed to understand not just how to use the system, but how to troubleshoot problems that could ground an aircraft. Number 172. Squadron received the first operational ASV Mark III aircraft in late February 1943. Number 407 Squadron RCAF followed shortly after. The initial patrols over the Bay of Biscay in early March found no submarines, but the radar operators gained critical experience. They learned to distinguish submarine contacts from fishing vessels and debris. They discovered that sea state affected clutter in ways different from ASV Mark II. Most importantly, they confirmed that the system provided no warning to U-boats until the moment of attack. The night of March 17th brought the first contact. Sergeant Harrington's 9-mile detection of a surfaced U-boat proved the concept worked operationally, not just in training exercises. The lee light failure prevented attack, but the U-boat had not dived, confirming that Metox provided no warning. The following day, March 18th, Wellington crews made the first successful attack using ASV Mark III. The submarine, taken completely by surprise, attempted to dive, but depth charges bracketed the boat before it could submerge. Coastal Command noted with satisfaction that U-boats were no longer disappearing from radar screens as aircraft approached. By the end of March 1943, 13 U-boat sightings had been made by ASV Mark III equipped aircraft. April would bring dozens more. The statistical impact became overwhelming. In the Bay of Biscay, U-boat sightings by Coastal Command aircraft had fallen dramatically in summer and fall 1942 after Metox deployment. By May 1943, sighting rates exploded to levels exceeding anything achieved before Metox existed. U-boats transiting through Biscay faced detection probabilities approaching certainty. Aircraft equipped with centimetric radar hunted submarines with a technological advantage as complete as any in military history. The German reaction revealed the psychological impact of fighting enemies with superior detection technology. U-boat commanders filed increasingly desperate reports. They described being attacked without warning by aircraft that appeared from darkness or clouds. They noted that Metox remained silent during approaches that should have triggered warnings minutes in advance. They reported multiple attacks per patrol, suggesting Allied aircraft possessed uncanny ability to locate submarines in vast ocean areas. Donitz convened emergency meetings with Germany's top radar experts throughout spring 1943. The discussions revealed fundamental misunderstanding of Allied capabilities. German scientists insisted that centimetric radar was impractical for airborne applications due to power generation limitations. The vacuum tube technology available, they argued, could not produce sufficient microwave power for militarily useful detection range. Metox should theoretically provide adequate warning against any operational Allied radar system. The experts offered alternative explanations. Perhaps the Allies had developed infrared detection systems that could sense engine heat from diesel exhaust. Perhaps they were using acoustic detection, though this seemed implausible at operational ranges. Some mentioned the theoretical possibility of advanced magnetron technology, but this was dismissed as beyond Allied manufacturing capabilities. If German engineers, with their superior technical training and industrial resources, had concluded centimetric radar was impractical, surely the British could not have solved the problem while enduring years of strategic bombing. One theory gained particular traction among German naval staff. Perhaps Metox itself was betraying U-boat positions. The receiver, like most radio equipment, emitted weak electromagnetic radiation during operation. Perhaps Allied aircraft carried equipment that could detect these emissions, turning Metox from protective warning system into a beacon guiding attackers to their targets. The theory had a certain logical appeal. It explained why attacks increased after Metox deployment rather than decreased. It accounted for the uncanny accuracy with which Allied aircraft seemed to locate submarines. The captured RAF officer's testimony would transform this speculation into catastrophic German miscalculation. But the groundwork for that deception was being laid by radar operators who discovered something unexpected about their new equipment, something that would later be formalized into the Vixen attenuator system and change the tactical balance even further in favor of the Allies. April 19, 1943. Coastal Command Development Unit. RAF Chivnor. Flight Lieutenant James Patterson sat in the cramped radar operator's position of a Wellington bomber, running yet another test flight over the Bristol Channel. The drill had become routine: detect the test submarine at maximum range, track it as the aircraft approached, coordinate with the pilot to position for a simulated attack run. Patterson had completed dozens of these exercises, but today something different caught his attention. As the Wellington closed from 14 miles to 9 miles, Patterson noticed the submarine contact beginning to fade on the display. Not disappear entirely, the U-boat was still clearly visible, but the return signal weakened noticeably. He mentioned this to the pilot, who confirmed they were maintaining steady altitude and approach angle. The target vessel reported no change in aspect or trim, yet the radar return was definitely weakening. Patterson experimented. He adjusted the transmission power control, reducing output slightly. The contact remained visible, still trackable, but weaker. He continued reducing power as they closed. At 5 miles, with transmission power at roughly half normal output, the submarine was still clearly detectable. Patterson realized what he was observing. The radar return strength was proportional to range, following the inverse square law he dimly remembered from technical training. But by progressively reducing transmission power as range decreased, he could maintain constant return strength on the display. More importantly, if German U-boats possessed detection equipment for centimetric radar and intelligence, suggested they were frantically developing such systems. Reducing transmission power as the aircraft approached might confuse their operators. A German radar detector would sense the signal growing stronger as the aircraft approached, then suddenly weakening, suggesting the aircraft was turning away or passing at a distance. By the time the U-boat crew realized they were still the target, it would be too late to dive. Patterson filed a detailed technical report describing his observation. The concept moved up through Coastal Command to the Telecommunications Research Establishment, where Robert Hanbury Brown and his team immediately understood the implications. They had already been considering attenuator systems as a response to anticipated German centimetric detectors. Patterson's field observation validated the concept and suggested the technique could be implemented through operator procedure even before dedicated attenuation hardware became available. The TRE engineers began designing a formal attenuator system that would give radar operators precise control over transmission power. 2 approaches emerged. The first, designated Type 53, used wire rings positioned in the waveguide between the magnetron and the antenna. When rotated parallel to the waveguide, the rings had no effect on signal propagation. When rotated perpendicular, they began to resonate and, through electromagnetic induction, opposed the original signal, progressively muting transmission power. The second approach used a shorting stub in the waveguide that could be adjusted to create a similar muting effect. Both systems presented challenges. The shorting stub changed the loading on the magnetron, causing output fluctuations that could affect target tracking. The rotating ring system required precise mechanical calibration to ensure smooth power reduction without sudden steps that might alert German operators. Neither system would be ready for production until late 1943. In the interim, radar operators like Patterson learned to adjust transmission power manually using the controls intended for system calibration, creating improvised attenuation that achieved similar results. This technique, later formalized and named Vixen, represented exactly the kind of innovation that comes from operators working with equipment rather than engineers designing it. Patterson had discovered through observation what theorists would have calculated mathematically. His practical fieldwork led to a tactical advantage that extended ASV Mark III's effectiveness even after German centimetric detectors eventually deployed. But the most consequential improvisation was about to occur in a German interrogation room where a captured RAF officer would provide testimony so perfectly crafted that it would derail German countermeasure programs for 8 critical months. The officer's name has never been definitively established in declassified records. What is known is that his aircraft was shot down over occupied territory in spring 1943, and he was captured by German forces. Standard interrogation followed. The Germans wanted technical information about Allied radar systems. They needed to understand why their U-boats were being slaughtered in the Bay of Biscay after months of successful operations. The officer, during interrogation, made a remarkable claim. He stated that Coastal Command aircraft no longer used radar for search. Radar was employed only during the final approach, in the last minutes before attack. Instead, aircraft were using receivers tuned to detect electromagnetic emissions from Metox detectors. These receivers could detect Metox radiation at ranges approaching 90 miles, far exceeding the detection range of ASV radar itself. U-boats running with Metox active were inadvertently broadcasting their positions to Allied aircraft, which would home in on these emissions before activating radar for the final attack. The testimony was technically plausible. Radio receivers do emit weak, electromagnetic radiation during operation, a property known as intermediate frequency radiation or oscillator leakage. Superheterodyne receivers like Metox are particularly susceptible to this effect. With sufficiently sensitive detection equipment, it was theoretically possible to locate an active Metox receiver at extended range. The physics supported the claim. German naval intelligence assessed the testimony. They recognized it might be deliberate disinformation, but they could not risk assuming it was false. If Metox was indeed betraying U-boat positions, continuing to use it would accelerate the catastrophic losses. The technical explanation seemed more plausible than admitting the Allies had achieved revolutionary advances in radar technology that German scientists insisted were impossible. On August 13, 1943, German Naval High Command issued an urgent message to all U-boats at sea. All U-boats. Attention, all U-boats. Shut off Metox at once. Enemy is capable of intercepting. Keep radio silence until further notice. Kapitänleutnant Herbert Werner, executive officer of U-230, later described the message's impact. We received this order while on patrol in the Atlantic. For months, Metox had been our only protection against radar-equipped aircraft. Shutting it off meant surfacing blind, unable to detect approaching aircraft until too late to dive safely. But headquarters insisted the device was betraying us. Better to run without warning than to broadcast our position to every Allied aircraft within 90 miles. The order created exactly the result Allied planners could have hoped for, but never dared to expect. U-boats stopped using their radar warning receivers entirely. This meant that even older ASV Mark II radar, which Metox could detect, became effective again for aircraft still equipped with the earlier system. U-boats that had routinely dived minutes before aircraft could close to attack range now remained on the surface, unaware of approaching threats, until searchlights or bombs announced the attack. The psychological impact proved even more significant than the tactical advantage. U-boat commanders no longer trusted their own technology. They suspected their equipment might be working against them rather than protecting them. This uncertainty infected every operational decision. Should they surface to recharge batteries? How long could they safely remain exposed? Was that aircraft silhouette on the horizon real or imagined? The confidence that had characterized U-boat operations during their earlier successes evaporated, replaced by caution that degraded operational effectiveness even when no Allied aircraft were present. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German scientists, meanwhile, redirected their efforts based on the false assumption that Metox emissions were being detected. They developed improved receiver designs that eliminated or minimized intermediate frequency radiation. The Wannsee system, introduced around August 1943, used crystal detectors that produced virtually no electromagnetic emissions. This solved a problem that did not exist while doing nothing to address the actual threat of centimetric radar. The delay proved catastrophic. Germany had captured an intact H-2S radar set when a Sterling bomber was shot down near Rotterdam on February 2, 1943, just days after centimetric radar entered operational service. German scientists examined the magnetron, determined its operating frequency, and understood immediately that existing radar warning receivers were blind to this technology. Yet, this information apparently did not reach the Kriegsmarine quickly enough to influence operational decisions. When it finally did reach naval intelligence, the Metox radiation theory seemed to provide a simpler explanation for U-boat loss. It was not until September 1943, 6 months after ASV Mark III deployment began, that Germany fielded a radar warning receiver capable of detecting centimetric wavelengths. The Naxos system, designated FU-MB7 Naxos-U for U-boat applications, could theoretically detect 10-centimeter radar emissions. but the system had severe limitations. Detection range was only 8 kilometers, too short to provide useful warning. The antenna required mounting on the conning tower, where it was vulnerable to sea spray and weather damage. Most critically, by the time Naxos deployed, the Battle of the Atlantic had already been lost. May 1943 marked the culmination of Allied technological dominance. That month, designated Black May by German submariners, saw catastrophic U-boat losses that forced Donitz to withdraw from the North Atlantic entirely. The statistics tell the story with brutal clarity. 41 U-boats were lost in May 1943, representing approximately 25% of operational submarine strength. These losses were unsustainable. Germany's submarine construction program, running at roughly 20 boats per month, could not replace losses at this rate. More critically, experienced crews were dying faster than training programs could replace them. The convoy battles that month demonstrated Allied dominance with shocking clarity. Convoy ONS-5, consisting of 43 merchant ships protected by 16 escorts, was attacked by approximately 30 U-boats in late April and early May. The Germans managed to sink 12 merchant ships, but lost 6 U-boats with 5 more severely damaged. For the first time in a major convoy battle, U-boat losses approached their successes. The exchange rate that had made the campaign viable had collapsed. 2 weeks later, Convoy SC-130 demonstrated complete Allied control. Of 38 merchant ships in convoy, 0 were lost, despite attacks by 25 to 30 U-boats from 3 patrol lines. The Germans lost 3 submarines. Aircraft equipped with ASV Mark III radar detected every attempt to approach the convoy, vectoring surface escorts to intercept U-boats before they could reach attack positions. The defensive systems that had seemed adequate in 1942 proved worthless against coordinated radar-directed defense. The Bay of Biscay became a killing ground. U-boats transiting to and from Atlantic patrol areas had to cross the bay, where Coastal Command maintained constant air coverage. Before centimetric radar, submarines could transit at night with reasonable safety, using Metox to detect approaching aircraft in time to dive. After March 1943, the transit became a gauntlet that few boats passed without incident. April and May saw 56 U-boats lost to air attack, many of them in Biscay. Donitz reported to Hitler that the situation had become impossible. The admiral ordered tactical changes that revealed German desperation. U-boats were instructed to transit Biscay in groups, on the surface during daylight, concentrating their anti-aircraft fire to drive off attacking aircraft. This suicidal policy cost more submarines than it destroyed aircraft. Allied aircraft could detect U-boats from beyond the effective range of anti-aircraft fire, call in additional aircraft or surface ships, and attack with overwhelming force. Submarines that stayed on the surface to fight were stationary targets. Those that attempted to dive became vulnerable to depth charges. On May 24, 1943, Donitz made the most painful decision of his career. He drafted the order that effectively conceded defeat in the Battle of the Atlantic to all U-boats at sea. Due to superiority of enemy location equipment and overwhelming air coverage, North Atlantic operations are temporarily suspended effective immediately. All boats currently in the North Atlantic are to withdraw to the position southwest of the Azores. Boats transiting to operational areas are to proceed to Biscay ports. Further operations will await development of improved detection equipment and enhanced anti-aircraft capabilities. The order marked the end of Germany's strategic submarine campaign. U-boats would continue operating in other theatres throughout the war, achieving occasional tactical successes. But they would never again threaten Allied supply lines in the way they had from 1940 through early 1943. The tonnage war, which had seemed so close to German victory just months earlier, had been decisively lost. The impact on Allied operations was immediate and overwhelming. Merchant ship sinkings in the Atlantic dropped from 82 ships in March 1943 to only 17 in June. Cargo deliveries to Britain stabilised. The massive build-up for D-Day and the liberation of Europe could proceed without fear that supplies would be interdicted at sea. The convoys that would support Operation Overlord began assembling in American ports, protected by technology that had rendered Germany's most effective weapon obsolete. The human cost of the battle receives less attention than the strategic outcome, but it was staggering. Of approximately 40,000 men who served in German U-boats during the war, roughly 30,000 died, representing a 75% casualty rate, the highest of any military service on either side. They drowned in steel cylinders crushed by depth charges. They suffocated when air systems failed under prolonged attack. They burned when diesel fuel ignited from combat damage. They died knowing their equipment was inferior, their missions increasingly futile, their sacrifice changing nothing in the war's strategic outcome. Kapitänleutnant Werner Henke, commanding U-515, achieved considerable success during his patrols, but was eventually sunk by U.S. Task Group 22.3 in April 1944. During interrogation at Fort Hunt, Virginia, Henke provided testimony that revealed the profound psychological impact of technological inferiority. The interrogation transcripts, declassified decades later, show a man broken not by military defeat, but by recognition of fundamental inadequacy. "We knew by mid-1943 that the war was lost," Henke told his interrogators. Not because German soldiers lacked courage or skill, but because Allied technology was systematically destroying every advantage we once possessed. The Metox detector became useless against the new radar. We called it the grave bell among crews, because when it failed to warn of approaching aircraft, it rung only for our funerals. Even later, detectors arrived too late for most boats. We could detect emissions at short range, while Allied aircraft detected us from beyond visual distance. We could dive when warned, but aircraft would circle overhead, calling destroyers to depth charge us. We could not escape what we could not see until too late. Henke's story ended tragically. Falsely accused of war crimes related to survivors of a merchant ship, his boat had sunk, threatened with extradition to Britain to face charges. Henke attempted to escape from Fort Hunt on June 15, 1944. He was shot and killed by guards, becoming the only prisoner to attempt escape from the facility during the war. His death, like so many others, represented a life consumed by a conflict decided ultimately by physics and engineering rather than courage or tactics. The technical developments that created Allied dominance continued evolving through the war's final years. By November 1943, British intelligence detected that U-boats had finally deployed centimetric radar detectors. The Naxos system worked as designed but provided such short warning ranges that it offered little tactical advantage. Allied scientists responded by developing 3-centimeter radar in systems that Naxos could not detect. The Americans fielded H-2X radar operating at 3-centimeter wavelength. The British developed ASV Mark 7, similarly operating in the X-band. These systems provided even better resolution than 10-centimeter radar, capable of detecting submarine snorkel masts protruding only feet above the water surface. Germany introduced the Type 21 electro-boot in desperate attempts to regain tactical parity. This revolutionary submarine design featured streamlined hulls, triple battery capacity, 17-knot submerged speed compared to 7 knots for conventional boats, and sophisticated sonar systems. Had Type 21 boats entered service in significant numbers during 1943, they might have extended the Battle of the Atlantic considerably. But rushed production created severe quality problems. Of 118 boats constructed, only 4 were fully combat-ready before Germany's surrender. Only 2 conducted combat patrols in April and May 1945, achieving no sinkings before the war ended. The final U-boat patrol demonstrated both the Type 21's potential and the futility of German technological efforts, arriving years too late. U-2511, the first Type 21 to see operational service, departed on April 30, 1945, commanded by Korvettenkapitän Adalbert Schnee, one of Germany's most experienced submarine commanders. On May 4, Schnee detected a British cruiser task force and executed a perfect attack approach. The boat's superior underwater speed and silent running capabilities allowed it to close to firing position undetected despite Allied radar coverage. Schnee did not fire. Germany had already announced surrender negotiations. He surfaced and radioed his position on May 5th, ending the U-boat war not with violence but with acknowledgement of defeat. In his post-war memoir, Schnee reflected on the bitter irony. "We proved that day what the Type 21 could have achieved had it entered service a year earlier. But such demonstrations were meaningless. The Allies had already won through industrial capacity and technological innovation deployed in 1942 and 1943. Our most advanced technology arrived when the war was already lost. The story of Allied radar dominance cannot be understood through technological specifications alone. The cavity magnetron produced 40 kilowatts of microwave power at 9.1 centimeter wavelength. ASV Mark III could detect surfaced submarines at 14 miles range. These are facts, measurable and verifiable. But they do not explain why the technology proved so devastatingly effective. The answer lies in the convergence of multiple factors that occurred simultaneously in early 1943. Industrial capacity to produce magnetrons in sufficient quantities. Operational deployment rapid enough to achieve strategic surprise. Innovative techniques like the Vixen attenuator, discovered by radar operators in the field. Intelligence operations that successfully deceived German countermeasure programs. Most fundamentally, the systematic application of scientific principles to military problems in ways that Germany, despite its reputation for engineering excellence, could not match during the critical period. The Metox deception deserves particular attention because it reveals how intelligence operations can amplify technological advantages. The captured RAF officer's testimony, whether deliberately crafted or fortunately interpreted, convinced German naval intelligence that their radar warning receivers were betraying them rather than protecting them. This led to operational orders shutting down Metox in August 1943, months before German scientists finally understood that centimetric radar was the actual threat. The 8 months between March and November 1943, when Germany operated largely without effective radar warning systems, represented the decisive period of the Battle of the Atlantic. During those months, Allied aircraft and ships equipped with centimetric radar achieved such overwhelming tactical dominance that U-boat operations became unsustainable. By the time Germany fielded Naxos detectors in November, Allied convoy defense had been perfected to the point where detection alone no longer guaranteed U-boat survival. The Germans were solving yesterday's problems, while new threats rendered their solutions obsolete. Personnel quality also played a critical role. The RAF radar operators and technicians who deployed ASV Mark III in early 1943 were among the most highly trained specialists in Coastal Command. They had spent months learning the new equipment. They understood electromagnetic theory well enough to recognize anomalies like the progressive power reduction technique that Flight Lieutenant Patterson discovered. They could troubleshoot complex technical problems while flying combat missions over hostile waters. This level of expertise, distributed across dozens of squadrons, created a force multiplier that pure technology alone could not achieve. The Telecommunications Research Establishment deserves recognition for its rapid translation of field observations into formal systems. Patterson's discovery of progressive power reduction in April 1943 became the formalized Vixen attenuator system by late 1943, a development cycle of roughly 6 months from field observation to production hardware. This responsiveness, the ability to incorporate operator feedback into improved equipment, gave Allied forces an adaptive advantage that German bureaucracy could not match. German technical response, when they finally arrived, revealed the organizational problems that plagued Nazi military development. The Naxos detector worked as designed but suffered from inadequate testing before deployment. The antenna mounting proved vulnerable to sea spray. The receiver electronics failed under the vibration and temperature extremes of submarine operations. The short detection range, only 8 kilometers, reflected fundamental limitations of receiver sensitivity that German engineers could not overcome with available components. Each problem could have been resolved with more development time, but time was the one resource Germany no longer possessed. The Type 21 submarine program exemplified similar issues. The design was brilliant, incorporating hydrodynamic principles that would influence submarine construction for decades. But rushed production to meet impossible deadlines created quality problems that made most boats unseaworthy. Welding defects caused hull breaches. Battery systems failed during deep dives. Hydraulic torpedo loading systems jammed under operational conditions. Again, these problems could have been resolved with adequate testing and refinement, but the strategic situation demanded immediate deployment of equipment that was not ready for combat. The contrast with Allied development programs could not be more stark. ASV Mark III entered service after extensive testing. Problems discovered during operational deployment received immediate attention. Magnetron production scaled smoothly from dozens per week to thousands per month. Training programs ensured operators understood both the equipment and the tactical doctrine for employing it effectively. Each component of the system, from hardware to personnel to operational procedures, received the attention required to ensure effectiveness. This systematic thoroughness, more than any single technological breakthrough, explains Allied victory in the Battle of the Atlantic. The cavity magnetron was revolutionary, but revolutions require more than invention. They require production at scale, deployment with adequate training, integration into operational doctrine, continuous refinement based on field, experience, and organizational structures that support rather than hinder innovation. The Allies achieved all of these. Germany managed only sporadic technical brilliance that could not be sustained at the strategic level. The personal stories of the men who operated this technology reveal human dimensions that statistics cannot capture. Sergeant Michael Harrington, whose detection of a surfaced U-boat on March 17th marked one of the first operational uses of ASV Mark III, continued flying patrols through 1944. He survived the war and later worked as a civilian radar technician, his wartime experience translating directly into post-war employment. Flight Lieutenant James Patterson, who discovered the progressive power reduction technique, received no special recognition for his innovation beyond a mention in technical reports. He was one of hundreds of radar operators whose individual contributions, small in isolation, collectively created the tactical superiority that won the campaign. The German submariners who survived the war carried psychological scars that lasted decades. Oberleutnant zur See Herbert Werner published his memoir Iron Coffins in 1969, describing the terror of fighting against superior Allied technology. Every patrol after May 1943 was a survival exercise disguised as a military operation. Werner wrote, "We understood that Allied radar could detect our periscope wake, our snorkel exhaust, even our conning tower wash. We travelled submerged far longer than boats were designed to endure, breathing foul air, conserving battery power, surfacing only when fuel and oxygen forced us. The Atlantic, which we had dominated in 1942, became an enemy more dangerous than British destroyers." Korvettenkapitan Peter Erich Kremer, who commanded U-333 through multiple successful patrols and survived the war as one of only 3 senior U-boat commanders to do so, published his Memoirs as U-boat Commander in 1984. He recalled a patrol in June 1943 that exemplified the changed tactical situation. "We detected an enemy aircraft at extreme range with our new Wannsee radar detector. I ordered immediate dive to 150 meters and rigged for silent running. We stayed down 6 hours, far beyond safe operational limits. When we carefully surfaced to snorkel, the same aircraft or another reappeared within minutes, forcing us down again. This pattern continued for 14 hours, until our batteries were nearly exhausted. We had to surface or suffocate. When we broached, the aircraft was waiting, positioned perfectly for attack. Only frantic anti-aircraft fire and a crash dive that nearly imploded the pressure hull saved us. We never fired a torpedo that patrol. We spent 3 weeks attempting to evade detection long enough to attack anything. Allied mastery of the technological domain was so complete we could barely execute our basic mission." The statistical summary of the Battle of the Atlantic confirms the decisive impact of centimetric radar introduction in early 1943. From January through May 1943, during the period when first-generation ASV Mark III was being deployed, but before full operational coverage was achieved, U-boats sank 245 merchant ships totaling approximately 1,289,000 tons. German loss during this period were 95 U-boats, including the catastrophic 41 boats lost in May alone. From June 1943 through May 1944, after centimetric radar equipped most Allied aircraft and ships operating in the Atlantic, merchant ship loss dropped to 185 ships, totaling approximately 819,000 tons, despite more U-boats being at sea. German loss during this period climbed to 237 U-boats. The exchange rate had reversed completely. In March 1943, at the peak of U-boat effectiveness, Germany sank 82 merchant ships, totaling 476,000 tons in the Atlantic, while losing 12 U-boats. By summer 1943, typical months saw fewer than 20 merchant ships sunk, while U-boat loss remained in double digits. The tonnage war had become unwinnable for Germany. American shipyards were launching Liberty ships at rates approaching 3 vessels every 2 days at peak production. Even with optimistic estimates of U-boat effectiveness, German submarines could not sink merchant ships faster than they were being built. The mathematical certainty of defeat was obvious to anyone who understood the production numbers. Dönitz understood. He continued operations because abandoning the Atlantic would free Allied air and naval forces for other theatres, hastening defeat on all fronts. But he knew that strategic victory in the submarine campaign had become impossible. The post-war assessment by military historians consistently identifies centimetric radar as one of the decisive technologies of World War II. The British official history of the war at sea states without qualification that the introduction of 10-centimeter radar in early 1943 marks the turning point in the Battle of the Atlantic. American naval historians reached similar conclusions. Samuel Eliot Morrison's 15-volume History of United States Naval Operations in World War II describes ASV Mark III deployment as the technological development that broke the back of the U-boat campaign. These assessments rest on firm statistical foundations. The correlation between centimetric radar deployment and the collapse of German U-boat effectiveness is too strong to be coincidental. The timing is precise. March 1943 saw the last major German successes against convoys. ASV Mark III deployment began that same month. April saw reduced German effectiveness. May brought catastrophic U-boat loss. By June, Dönitz had withdrawn from the North Atlantic. The causal chain connecting radar deployment to strategic outcome is direct and undeniable, but the story is ultimately about more than technology. It is about how innovation happens in the pressure of wartime necessity. Flight Lieutenant Patterson did not discover progressive power reduction through theoretical analysis. He noticed an anomaly during routine testing and investigated its implications. The captured RAF officer did not craft his Metox testimony according to some master deception plan. He provided plausible technical information that German intelligence chose to believe because it fit their expectations better than admitting Allied technological superiority. These human decisions, made by individuals responding to immediate circumstances rather than following grand strategies, collectively created the technological dominance that won the Battle of the Atlantic. The cavity magnetron was a revolutionary invention, but its war-winning impact came from how it was deployed, improved, and integrated into operations by hundreds of technicians, operators, and engineers whose names appear in no history books. The organizational lesson is perhaps the most important. The Allies created systems that encouraged innovation from below. Radar operators could file technical reports that would be read by engineers at TRE. Field observations could influence production designs within months. Problems discovered during operations received immediate attention from technical specialists. This feedback loop, connecting frontline operators to research establishments to production facilities, created an adaptive system that continuously improved its own effectiveness. Germany lacked this organizational structure. Technical development remained centralized in facilities that had limited contact with operational forces. U-boat commanders filed reports describing Allied capabilities that contradicted what German scientists believed possible. The reports were dismissed or rationalized rather than investigated. When captured equipment finally proved Allied technological advantages were real, the response was slow and inadequately resourced. The organizational barriers to innovation proved as insurmountable as the technical challenges. The lasting impact of centimetric radar extended far beyond World War II. The microwave technology developed for military applications became the foundation for post-war telecommunications. Satellite communications relied on microwave links developed from wartime research. The domestic microwave oven, descended directly from magnetron technology, became standard in homes worldwide by the 1980s. The industrial expertise developed for wartime radar production enabled the electronics revolution of the 1950s and 60s. Companies that manufactured radar components transitioned smoothly into commercial electronics production. Engineers who learned microwave theory through military applications brought that knowledge into civilian industry. The massive investment in radar research during the war created technological capabilities that drove economic growth for decades afterward. The intelligence lessons proved equally lasting. The Metox deception demonstrated that adversaries can be manipulated through plausible technical information that confirms their existing beliefs. This principle influenced Cold War intelligence operations and remains relevant in modern strategic competition. The willingness to deploy revolutionary technology, despite capture risks, became standard policy. The operational advantages from fielding new capabilities quickly outweighed the risks that adversaries might copy them, provided that industrial capacity could maintain quantitative advantages. For the radar technicians and operators who fought the Battle of the Atlantic, the war's end brought mixed feelings. They had won a campaign that saved thousands of merchant seamen's lives and ensured the supplies needed for D-Day reached Britain safely. But they had also participated in slaughter on an industrial scale, destroying U-boats whose crews died by drowning or suffocation in crushed steel hulls. The technological dominance they had achieved made killing efficient and impersonal, reducing human beings to radar contacts that could be prosecuted with depth charges or bombs. Sergeant Harrington, interviewed decades after the war, described the psychological complexity of his wartime service. "We celebrated every U-boat kill because it meant fewer merchant ships would be sunk, fewer convoys would be attacked. But we also knew that each contact represented 40 or 50 men drowning in darkness, hundreds of feet underwater." The radar screen showed only abstract blips. It did not show the human cost. Perhaps that was necessary. Perhaps we could not have done our jobs if we had to think about the men dying at the other end of each attack. But it has never sat easily with me. The German survivors carried even heavier psychological burdens. They had fought with extraordinary courage against overwhelming technological odds. They had continued operating long after strategic defeat became obvious, sacrificing themselves to delay inevitable Allied victory by days or weeks. The 75% casualty rate among U-boat crews exceeded loss in any other military service. These men deserved recognition for their bravery, even as their cause deserved defeat. The final accounting must acknowledge both the Allied achievement and its human cost. Centimetric radar shortened the Battle of the Atlantic by months, possibly years. This prevented hundreds of merchant ships from being sunk and saved thousands of merchant seamen's lives. It ensured that supplies reached Britain in sufficient quantities to sustain both the civilian population and military operations. It enabled the massive build-up for D-Day to proceed without fear of interdiction at sea. By any strategic measure, the technology was decisive, but roughly 30,000 German submariners died fighting against this technological advantage. They were not evil men. They were not monsters. They were sailors doing their duty as they understood it, caught in a war their nation started but they had not chosen. Their deaths were necessary to achieve Allied victory, but they remained tragic nonetheless. The technology that made killing them efficient did not make their deaths less real or their suffering less profound. The radar operators who detected them, the pilots who attacked them, the depth charge crews who killed them, all participated in necessary violence. The moral complexity of that participation does not diminish with time. Technology can make war more efficient. It cannot make war less terrible. The men who developed, deployed, and operated centimetric radar understood this, even as they celebrated its effectiveness. They had helped win a campaign that saved civilization from Nazi tyranny, but they had done so through methods that remained fundamentally destructive regardless of technological sophistication. The story of how one radar technician's observation led to the Vixen attenuator, how one captured officer's testimony derailed German countermeasures, how hundreds of operators and maintainers turned revolutionary equipment into decisive tactical advantage, is ultimately a story about human ingenuity applied to human destruction. The ingenuity deserves recognition, the destruction deserves remembrance. Both are necessary to understand what happened in the North Atlantic between March and May 1943, when electromagnetic radiation generated by cavity magnetrons changed the course of history. In the decades since the war, historians have debated the relative importance of various factors in Allied victory. Industrial capacity, code-breaking, tactical innovations, strategic decisions. Each contributed, but the statistical evidence and the testimony of participants point consistently to one conclusion. When U-boats could no longer operate safely on the surface because centimetric radar made them visible to enemies they could not detect, the campaign became unsustainable. Everything else, from improved anti-submarine weapons to better convoy tactics to ultra-intelligence, built upon this fundamental advantage. The cavity magnetron created that advantage. The technicians and operators who deployed it turned potential into reality. The organizational systems that encouraged their innovations amplified individual contributions into strategic dominance, and the German failure to match or counter these developments, despite possessing scientists and engineers of equal capability, revealed that organizational effectiveness matters as much as technical brilliance in modern warfare. Percy Spencer's wartime achievement in manufacturing magnetrons at scale receives less attention than his accidental invention of the microwave oven. Flight Lieutenant Patterson's discovery of progressive power reduction remains buried in technical reports that few historians have examined. The captured RAF officer, whose Metox testimony derailed German countermeasures, remains unnamed in declassified documents. These men, and hundreds like them, changed history through actions that seemed small at the time, but proved decisive in aggregate. Their story demonstrates that wars are won not through individual genius, but through systematic application of collective expertise. The Allies built systems that identified, developed, and deployed technological advantages more effectively than their adversaries. They created organizational structures that encouraged innovation from operators and technicians, not just scientists and engineers. They maintained feedback loops connecting the battlefield experience to research establishments to production facilities. They fielded new capabilities rapidly while refining them continuously based on operational results. Germany, despite its reputation for engineering excellence and scientific achievement, failed at each of these organizational challenges during the critical 1942 to 1943 period. The consequences of that failure appear starkly in the casualty statistics. 30,000 German submariners died. Hundreds of U-boats were destroyed. The Battle of the Atlantic was lost, and the war continued for 2 more years with outcomes increasingly predetermined by Allied advantages in technology, industry, and resources. The electromagnetic spectrum, invisible to human senses but fundamental to modern warfare, became the battlefield where victory was won and defeat was sealed. The men who fought there with radar sets and magnetrons, waveguides and cathode ray tubes deserve recognition alongside those who fought with more traditional weapons. They shortened the war. They saved lives. They demonstrated that in modern conflict, physics and engineering matter as much as courage and tactics. The lesson remains relevant 8 decades later. Technology continues advancing. New domains of warfare continue emerging. But the fundamental principle endures. Successful military organizations must identify emerging technologies, develop them with adequate resources, deploy them with appropriate training, refine them based on operational experience, and maintain organizational structures that support rather than hinder innovation. The Allies did this in the Battle of the Atlantic. Germany did not. The results speak for themselves in the wreckage of U-boats scattered across the ocean floor and the merchant ships that reached port safely because the submarines that should have sunk them were destroyed first by radar-directed attacks. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.